I recently did a video showing how to format numerical values in a text box, showing the leading and trailing zeros and whatnot. Something I discovered while preparing that video is here I have a real number as a floating point integer, and if I increase it, I have some structured text. So if I press the button, I'm going to increase that number by 1. If I press the down button, I'm going to decrease it by, I'm sorry, by 1/10. So if I come up here, so it didn't increase by exactly 1/10. It increased by 1.0000149, blah, 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 blah. And if I add 1 to that, and I add 0.1 and I add 0.1, that error is compounding several decimal places out to the point where if I increase this rapidly, you can see it, the error starts getting into some digits that may actually be significant. So if we were using this to display some measurements, if we were using some kind of a digital scale, maybe we're measuring something to the 10,000ths, this number here would be rounding up, and we would have an error of possibly plus or minus 1/10,000th. So that's probably not desirable. So there's a website I'll link in the description how to get to this website, but it's a calculator showing a decimal input, and then it will output a 32-bit or 64-bit floating point variable. So you will be able to see with more precision exactly what the value is. So if I go 0.1, you can see here I have 0.100001490. So that was the same number that we had when we were looking at the visualization in Codesys. And the reason for that is because of the conversions. Here you see this is the binary representation of 1/10. And at 32-bit resolution, 1/10 doesn't resolve evenly. So imagine if you were measuring something with a tape measure that only has markings for eighths of an inch, and you were trying to measure something that was, say, 1/10 of an inch. Well, 1/8 of an inch is 0.125, and that's all that the tape measure can measure, but you're trying to measure 0.1. So there's going to be an error of 0.025. So we have the same thing here with our 32-bit floating point, converting binary to decimal. We have, it's about 9 places. We have some stray numbers, and that's just because of the way the conversion's being done. So if we look at a 64-bit double, this would be an L real in Codesys. You can see we get a lot closer. The number of zeros are out. I don't know. That's I don't know, 15, 16 decimal places. So let's jump over to Codesys and look at a visualization. So here we have a real number, and here we have an L real. And every time I press the button, I'm adding 0.1. So you can see here we've got that 0.149 out there. That was the same thing that we saw here, right? So those numbers match up. And I'm not displaying all the digits that that calculator shows, but we have the same error. So if we go up again, up again, up again. So something interesting right here, we ended on exactly 0.5. If we come back here and I put in 0.5, we get an even 0.5. So there's a binary representation that represents 5/10. And you can see that both in the real and the L real. But if we go up more, so it looks like the L real, our long floating point integer, our 64-bit, is able to display a number that's more accurate. It doesn't have this compounding error that we see in the real number. But if we increase this number pretty rapidly, now you can see the compounding error by adding 0.1, which is not an even binary number. It doesn't resolve to an even binary number. And we add 0.1 and we add 0.1. We're adding 0.1. So every time we add 0.1, we add 0.1000149, blah, 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 blah. We add all of this. So over several iterations, now we've added something that we didn't necessarily expect. And the 64-bit integer or 64-bit floating point is more accurate than the 32-bit in the way that it handles that, because we're more accurate, more places, but it's still something that compounds. So one way to handle this error is to count using an integer. We can add exactly 1 to an integer, and that's no problem. And then we can divide an integer by 10, and that will give us a more accurate representation, because we're doing the conversion from a whole integer number to a floating point decimal number after we've added. So if we, instead of adding 0.1, we add 1. So here I'm adding 1 to an integer instead of 0.1 to a float or an L float, and I'm subtracting 1 instead of subtracting 0.1. So I'm subtracting or adding an even full number, an integer. So if I go 1, 2, 3, so you can see the math here is scaling exactly as we would expect, where just using the real floating point number, we do have some error. And this is actually pretty accurate. You can see I'm displaying several decimal places here. I've counted up, and our L real is still displaying without any error. The rounding is happening, way out here beyond. I think I'm showing 17 decimal places. So they're both counting pretty good. Now here, our L real, our 64-bit is starting to show some error, but we're still out. I don't know, we're 13, 14 decimal places out here. But where we're doing an integer, we're incrementing an integer by 1 and then dividing it by 10, we've got exactly the number that we expect. And this is actually, it's going to fall apart when we get up into around 120. Okay, so here at 109, it should be 109.6, but we've got 109.599999. So if we jump back here, 109.6, we can see 109.6 cannot be represented evenly as a binary floating point decimal. So it's 109.599 as a 32-bit, as a 64-bit. It's the same thing. We've got a repeating 9 out more places, but it doesn't resolve to exactly 109.6. So Codesys is behaving exactly as we would expect it to, but it's not exactly what we'd expect based on our normal fundamental understanding of decimal mathematics, addition and subtraction, because we're converting a number from an integer into a binary number. So one way we can get around the limitation, if you look at an image of a standard, just a basic handheld calculator, the display on the calculator will only show 8 places. So what I've done here is this is the same number that we're displaying in this box, L real, that we've converted from an integer divided by 10. And I've just limited the display to 8 decimal places. So now if we start counting up, so we're at 0.92, it should be 92.1, and we've got 92.0999999. There's a repeating 9. But then here where we have the display limited to only 8 decimals, we have repeating 9 to 8 decimals, and the next number is a 9. So it's going to round up to 92.1. And we can see that if we keep counting 115.0999, again, it's going to round to 115.1, which is 1151 divided by 10. Hopefully this will help as you're developing your visualizations. If you have any questions, please post those in the comments.